back. This is Mr. Hassan's Maths channel. I'm now answering question number 2 from the June 2023 Statistics S1 paper from Edexcel International A-Level. This question here is about correlation and regression. It says 2 students, Olive and Shan, collect data on the weight W grams and the tail length T centimeters of 15 mice. Olive summarized the data as follows. STT equals 5.3173 and so on. They've got some summarized data. Calculate the value of STW and SWW. Now here, a lot of students will look at this and say this is some other language that is being, described here, right? But in fact, it's actually quite easy, especially when you have the formula sheet with you, right? So we need to find STW. And what does this STW mean? Basically, it's a measure of the variance, how spread apart the values of T are with W. Okay, basically what we have here, if we think about what we're going to have, I'll just make a little explanation for those of you who totally, completely have no idea what this topic is about. You have like a table of values, right? And you have table of values dealing with the weight, and also the tail length. So weight is W and tail length is T. And they've collected some data about the weight. There's 15 mice, so you have 15 pieces of data. Okay, so there's 15 mice. They've taken the weight of the mice. All right, so you've got the individual weights here of the mice, and you got the tail length of those mice. So that's the data that we have, right? So STT is basically the variance of these values, how spread apart the values are of the T values. STW is what is the variance between the W and the T. That's called the covariance of W and T, how spread apart they are as compared to each other, you could say. And SWW is the variance of how spread out the values of W are. It's a measure of how spread apart they are. That's what this S stands for, right? Now, to find STW and SWW, what we need to do is refer to the formula sheet, which I have got some extracts of it here. Hopefully that will help us. Nothing in the clipboard. Okay, so no problem. I copied it. What happened there? I copied them, but then they didn't save. Anyway, I'll go back to the formula sheet. The formula sheet is over here, right? What we're really interested in is these here, okay, for the first part of the question, SXX, XYY, XXY, right? So we're going to take these. I've just got a little copy of them there, and I'm going to place this over here. Okay, we're going to be using these formulae to find out what we need to find out. So let's look at STW. STW would be kind of like relevant. What would be relevant here is here you have SXX. Like you could say this is the X, this is the Y, for example. So this would be WW, STT. This would be STW. It's where you have the covariance. So what we're interested in is actually this formula here. Okay, because we have the summary data that will help us to use this formula here. Okay, so what does all these things mean as well? I'll just quickly go into that. The sum of W squared basically means you take the W values, you square each of them, and then add them together. That's how you get the sum of W squared. The sum of W would be where you just add the W's together. The sum of TW would be where you multiply T and W together first. So you for example, you have column TW, and you would add all those products together. And the sum of T would be just the sum of the T values. That's what these represent, okay? So here what we're going to do is we're going to have the sum of, it says XY, but actually we need TW, okay? The sum of T times W, minus the sum of T times the sum of W over N. N is the number of entries which we have for 15. N is 15 here, because there's 15 mice that were monitored. Okay, so now what we need to do is we need to just put the correct values in from the equations that we have. So we can say that STW is going to therefore be the sum of TW, which is going to be 2,304.53 minus the sum of T, which would be 114.8 times the sum of W, which would be 297.8 over the N, which is 15. Okay, so that's going to give us what we're looking for. Okay, over there, which is the answer, which then we round to 3SF at the end. So STW is going to be, so I'm going to have 2,304.53 minus, and you've got your fraction 114.8 times 297.8 over 15. Okay, so that gives you, let me just make sure I did that correct. That gives you 25.367, 25.367. Okay, so we know that that's going to be STW, therefore, to 3SF will be 25.4. Okay, that's STW, right? We have to also find SWW. So for SWW, we're going to use, for example, SYY. We'll use this. Okay, so we're going to have the sum of W squared, which we have, which is, I'll just put it so we can see the sum of W squared minus the sum of W, which is then squared. That's the difference. There's a difference between these two. Okay, they're not the same. This is the sum of the squares of each of these W values, and this is the sum of all the W values and then squared. Okay, so this is going to be 6,889, 0.12 minus 297.8 squared over 15. Okay, so that will give us our value. So we have 6,089, 0.12 minus we have 297.8 squared, and that's divided by the number, which is 15. So very carefully, don't put in the wrong numbers here. It's easy to just type in an incorrect number or forget a decimal point or something, so be careful. 176.797, 176.797, which will give us then for SWW, it will give us 177 to 3SF. Okay, they didn't tell us how to write it, so we write it to 3SF as we are told in the beginning paper. Front cover tells us non-exact values to 3SF. All right, so that's part A done. Now we're going to go on to part B. It says calculate the value of the product moment correlation coefficient between W and T. The product moment correlation coefficient, PMCC, which is given the symbol R. And all this is basically is a measure of how spread out the plots is away from the line of best fit. So when you have your W and your T, okay, and you plot the points, okay, W against T, you end up with some sort of a scatter plot. And the line of best fit would be a line that passes with the best fit through those points. Okay, that's the line of best fit. Now the BMCC tells us basically how close those points are to a straight line. It tells us, the sign of it tells us the correlation in terms of is it negative or positive. It's positive. If R comes out as positive, it means positive correlation. Negative, it means negative correlation. And the value of R indicates to us how strong the correlation is. If it's close to 1, the PMCC always ranges between -1 and 1. The closer it is to 1, the closer it is to perfect positive correlation, means the points will be in an exact straight line in the positive direction, okay, positive gradient. And if it was a negative one, it'd be perfect negative correlation, meaning they would be in a perfect straight line, but with a negative gradient. And the closer you are to 0, then the points are all over the place. There's not really any correlation between them. So the PMCC tells us the strength of the correlation between the variables that we have. And to find the PMCC, there's a very simple formula, which is over here, that we can use. Have I got it here somewhere? Here it is. This is the relevant formula that we need. They've given you all these different formulas, which are basically the same as, I mean, this is how you find SXY. This is how you find SXX. So it's basically the same things as we had above, but this is like the summarized version of the formula that we need. And that will help us find the PMCC. So we need to have these values, which we already calculated or given in the previous part of the question. So basically, the value of R is given by SXY, which in this case is going to be STW or WT, how do they call it? STW. Okay, so we need STW, which I think we found already, over the square root of STT times SWW. And all of those things we have. So STW is what we found earlier as, I'm going to write it in its more precise form, which is 25.3673. 25.3673 over the square root of STT, which we're already given in the question. Okay, STT was 5.3173. Okay, 5.3173. 5.3173 multiplied by, and then you have SWY. SWY is what we calculated. SWY is basically SWW, which gives you 176.797 to, in its more accurate form, 176.797. So that will give us the value of R. So we could have saved those previous two values to use them in the exact form, but there's not a problem because this is enough decimal places to make it more accurate than we need. So we have 25.3673 divided by the square root of 5.3173 times 176.797. And that will give us the value of R, which is 0.82735. 0.82735. So we can say R is equal to 0.827 to 3SF. Okay, they didn't say otherwise, so we write it to 3SF. That shows that there is positive correlation and it's pretty strong. It's closer to 1, so it's pretty strong positive correlation, meaning that there is some sort of link between the tail length and the weight of the mice. Okay, the ones which have greater weight tend to have greater tail lengths as well. That's what that indicates. It's quite positive correlation between that data. Then it says, show that the equation of the regression line of W on T can be written as the following. So basically now, this is telling us to find the equation of this straight line, the equation of the line of best fit. That's what they're telling. The regression line means the line of best fit. Of W against T, they want W to be the Y and T to be the X. So W, as I've drawn here, W is going to be the Y-axis, T is going to be the X-axis. That's how they want the equation to be set up. So the regression line of W on T, okay, of Y on X. If you look at the formula sheet, which again, I'm going to take what we need from here. All right, we got the regression line of Y on X is given by this, and also something else which is relevant from there that will help us. Okay, so let me just put this here. So that we're told that the regression line of Y on X is B equals SX over SY. So the regression coefficient of Y and X. So the least squares regression line of Y and X is given by this formula. So this is the formula that we're interested in first. The least squares regression line means the line of best fit of Y on X is given by this formula here, where Y equals A plus BX. Okay, in our case, okay, we're going to have y equals a plus bx, y on x, our y is going to be w, and our x is going to be the t. So it's going to be w equals a plus b times t. So we have to find the value of a and we have to find the value of b. Now they told us a is equal to the mean of y. Now remember, the mean of y means the mean of w minus b times the mean of x. Our x is t, so it's going to be the mean of t. So to find a, which is like, you could say, the y-intercept, y equals mx plus c, all right? This is like the y-intercept. So to find a, we need to use the mean of y, and we need to use the mean of x, but we need to know what b is as well, okay? So the mean of y and x is no problem, because the mean of y would be the mean of w, which would be this divided by 15. The mean of x is the mean of t, which would be this divided by 15. The mean is the sum divided by the number of entries, right? So for that's no problem, but we have to find what b is. Okay, for us to proceed, we need to know what this b is, and they told us the regression coefficient of y on x is b equals sxy over sxx. So we can say b is equal to s. Now instead of xy, we're going to have tw over sxx. Now our t is our x, so it's going to be stt. That's going to be the value of b, which seems to be like the gradient of this curve. So stw, we already have, we found it, 25.3673. So 25.3673 over S double T, which is something that they gave us, I think, already. Yes, 5.3173. 5.3173. 5.3173. That's going to give you the value of B. Okay, so I'm going to put this in the calculator. So we have 25.3673 over 5.3173. That gives us 4.77. Okay, so I'll write it like this, 4.77 to 3SF. Okay, in fact, I'll write it more so we know that it becomes 4.77 to 3SF afterwards. Okay, so that's the value of B. So now we need to find the value of A. So we know that A is equal to the mean of Y, which is, as we said, our Y is W, so it's the mean of W minus B times the mean of T. So we can say A is equal to the mean of W, which is going to be the sum of W, which we know from up here, which is 297.8. That's 297.8 over 15 minus B times, and I'm going to take B in this form. I'm going to take B in this form, 25.3673 over 5.3173 times the mean of T, which is the T values added together, which we already were given as 114.8 divided by 50. 114.8 divided by the number of entries, 15. That's going to give you a value of A. Okay, so I'm going to use this fraction in this form, which I already have in my calculator like this. So I'll multiply that by 114.8. Was it 114? I didn't write it very. 114.8 over 15. Okay, and then I'm going to that's going to be that, and that has to be negative. All right, because it says minus, and I'm going to add to that the fraction 297.8 over 15, which is the mean of W. And that will give me the value of A, which is negative 16.658, negative 16.658. Okay, 85. So we can say, therefore, okay, our equation of line of best fit is W equals negative 16.7 3SF plus B times, which is 4.77 times T. So this is the equation of the regression line for W against T. Okay, that's the equation of the line of best fit, right? The line of best fit that we just discussed over there. Then it says, given interpretation of the gradient of the regression line, the gradient of the regression line, okay, which is the value of b, okay, is basically tells you that if we think about what we have here, interpretation means in context of the question. So w is the weight and t is the tail length. So what we can say is that, w against t is the change in w over the change in t. So as the tail length increases by 1 centimeter, okay, remember this is in grams and this is in centimeters, this is in grams and this is in centimeters. So with each 1 centimeter increase of tail length, the weight will increase by this much, 4.77. So we can say for each increase of 1 centimeter in tail length, the weight, okay, of the mouse increases by 4.77 grams. Okay, so for each increase of 1 centimeter in tail length, the weight of the mouse increases by 4.77 grams. It's like 4.77 over 1. The change in y over the change in x. The change in the tail length, okay, the change in the weight is going to be 4.77 for every 1 increase in the tail length. Okay, so there's part D done of this question. So that's A, B, C, D. Let's have a look. Is there another part? Part E. It says, explain why it would not be appropriate to use a regression line in part C to estimate the weight of a mouse with a tail length of 2 centimeters. Okay, now the appropriateness of regression lines and equations of regression lines is normally used in the case where we have the actual data and we can see that the data value that they asked us to use is out of the range of the data values that they gave us. So normally we would have the values of W and T, okay, and the T value that they give us doesn't fit in with the data values that we have. So for example, it could be the lowest data value was 5 and the highest data value was 10 or something like that, and 2 is not within that range. Therefore, it would not be appropriate to use the regression line for that value because it's something that's extrapolating out of the data that we have got, whereas interpolation is something which would be appropriate. Extrapolation is inappropriate. However, they didn't tell us exact values of the data. We don't know what the data values are. I guess we could work out the mean and maybe work out the standard deviation and then work out how far away this value is from the mean, how many standard deviations away from the mean, is it an outlier, is it something that's outside of the rest of the pieces of data. We could do that, but that's a bit much to ask for 2 marks. So what I'm guessing we should do here, which would probably be a better option, would be go and get the equation of the regression line, which was minus 16.7 plus 4.77t. So we have W equals negative 16.7 plus 4.77t. And if we replace the t with 2 centimeters, with 2, that should give us a weight. And does that give us a sensible answer? Yes or no? 4.77 times 2, it's going to give us a negative answer. We can see from the y-intercept, obviously, you can't have a negative weight. So it's going to be something where, there'll be some values for which the weight is going to become negative, some tail lengths, which will be negative according to this line of best fit, which probably only works well with a certain range of values of the actual weights of the mice that were measured. So we can see this is going to be a negative value for sure. If we work out what this is going to be, it's going to be negative 16.7 plus 4.77 times 2, which gives us a negative 7.16. So that's negative 7.16, okay, grams. So therefore, we can say that using, okay, t equals 2 centimeters gives a negative value for the weight for W, which doesn't make sense in reality. Therefore, okay, the regression line, make a conclusion, sorry about my bad writing, is not appropriate for t equals 2 centimeters. Okay, something like that. That's 2 marks. That's fine. All right. So part F says Shan decides to code the data using x equals t minus 6 and y equals w over 2 minus 5. Write down the value of the product moment correlation coefficient between x and y. Now, this is the value of R. Now, the data that we got before, what does it mean by being coded? Well, we have W and we have T, okay? Or we can say T and then W. Doesn't matter which one we write first. Okay, and what they've done is they've taken the W values, they've divided by 2, and then they've subtracted 5, and they gave us the Y value. Okay, and then they've taken the T values, they've subtracted 6 from them, and they gave us the X value. And then they've worked out using, the new data, the coded data, the value of the PMCC. They found the sum of the Y's, the sum of the X's, the sum of the X times Y's, the sum of the Y squareds, the sum of the X squareds, and so on. And they've worked out the same way that we did before, the value of R. Now, what we should understand is that R, the PMCC, is completely unchanged with any type of linear coding. Linear coding means coding that involves subtraction or division or addition, subtraction or multiplication, any of those types of codings. So if you change the values by subtraction, multiplication, division, all right, these types of operations, it will remain unchanged. So R will be the same value as we found in the previous part of the question, which was 0.827. So we just have to write down 0.827, and that's our answer. And there's part F, okay? It's unchanged by coding. You can say unchanged. We don't have to even write this down, but I'll just will by linear coding, okay? If you change it by squaring values and stuff, that's different. But if you change it just by addition, subtraction, multiplication, division, then there's no change in the value of R. Okay, so then it says write down an equation of the regression line of y on x. You do not need to simplify the equation. So basically, we take our original regression line, which we have here, w equals minus 16.7 plus 4.77t. So we have the original one, which is w equals minus 16.7 plus 4.77t. And we want to replace the w with what w is equal to, and the t with what t is equal to 2. So if we have y equals w over 2 minus 5, and we want to, make w the subject of this, we'll have y plus 5 equals w. So w over 2, sorry, then multiply by 2. So you have w equals 2y plus 10. So the w can be replaced by 2y plus 10 equals minus 16.7 plus 4.77 times t. Now we know that t is equal to, x is equal to t minus 6. Therefore, we can say t is equal to x plus 6. So I can just replace this with x plus 6. It says do not simplify your equation. That's enough for us to write it like this. Okay, if they wanted us to write the regression line of y on x fully, we would then rearrange this to make y the subject. We'd expand the bracket, subtract 10 from both sides, divide everything by 2. But here it tells us clearly you do not need to simplify your equation, and that can be left as that. And there is our answer. And that completes this question, which is question number 2 from the June 2023 statistics paper from International A-Level Edexcel. Other questions from this paper can be found in the playlist, which will appear in this part of the screen at the end of the video. Other questions dealing with the topic of correlation and regression will also be found in the playlist that will appear in this part of the screen. You can subscribe to my channel by clicking on the link that will appear here. And the video that will have a link over here will tell you how to use my channel to find what you're looking for. Thank you for watching, and see you soon.